geographers. Year 12s, new topic, tectonic hazards. And I'm a bit steaming because I have just recorded this full video, which took me 30 minutes. But unfortunately, I had the headphones jack plugged into the computer rather than the microphone jack. So I've got to do it all over again. Pants. Right, here we go then. So what are you going to learn? Well, the first thing you're going to learn is to plug the microphone jack into the computer carefully if you're ever recording a video. Right. The global distribution of tectonic hazards and the reason for this distribution. So if we look at a world map, we need to be able to describe where earthquakes, volcanoes and tsunamis occur, and we're going to have some understanding of why that is. Alright then, so if we look at the spec, so you know I'm not teaching you things you don't need to know, because that's the sign of a bad well, not the sign of a bad teacher, but yeah. The sign of a teacher that's got too much time. So, global distribution of tectonic hazards, or seismic hazards, can be explained by plate boundary and other tectonic processes. The hazards are earthquakes, volcanoes and tsunamis. We're going to know the different type of plate boundaries that cause these tectonic hazards. And we're also going to look a little bit as well at the intraplate processes, which all intraplate means is the centre or middle of tectonic plates. Right, we're also going to touch on the magnitude as well, because that's important. It's not just where the earthquakes happen, but it's their kind of severity, if you like, the amount of energy they release and how severe they are. Yeah. So obviously, I'm guessing that you've heard of scales such as the Richter scale or the moment magnitude scale. So yeah, we get kind of higher magnitude earthquakes at some plate boundaries compared to others. One thing I'm going to add as well to these videos from now on is in preparation for paper 3, where they test your paper 3 tests your ability to make links between topics, which we call synoptic links, consider the role, actions, motives, attitudes of key players and stakeholders, and how that might lead to different future outcomes. But the third way of getting synopticity is through 12 concepts or themes which cut across all topics. So 2 concepts or themes that cut across, or that I'm going to address or touch on this lesson, is cause and effect. So your physical geography, what's happening at plate boundaries to cause earthquakes and volcanoes. Yeah, in fact, I probably don't touch on that until a future video, but yeah. And risk, which is a population's exposure to harm or a hazard. Yep, so this one will cover risk. Right, my lot, in your Key Area 1 booklet, what I want you to do, as well as making notes, you should have everything you need in this video to do a bit of a tidy up and complete all the tasks up to page 7. Alright, so student tasks 1, 2, 3 and 4 in your booklets you should be able to fully complete after you've watched this video. Alright then, let's rock and roll. Right, plate boundary types. What we got? Let's have a nosy. These don't change really from Key Stage 3 to GCSE to A level. Terminology might be slightly different, but yeah. So what are they? Well, the first type of plate boundary is where 2 tectonic plates spread apart. And if 2 things are moving apart, then a big word we can use is divergent. These also, you might hear me refer to these as constructive as well. constructive plate boundaries. So you need to kind of switch and be able to recognize both. And I need one of them magic pens because you just cannot write with a mouse. It's impossible. So constructive or divergent means plates are moving apart. The second type is a transform or a conservative plate boundary. And that means the plates are sliding past each other. Now, here's the important distinction. They might be moving in opposite directions, like we can see in this graphic, where this plate is moving downwards and this plate is moving northwards. Or they could also be sliding past each other in the same direction, but at different speeds. So the one on the left is also moving up. The one on the right is moving up. It's just that one is moving faster than the other. And then you've got convergent plate boundaries, where two plates are converging or moving together. Yep. Okie dokie. Right. If we have a look at a world map of the major tectonic plates, we can see that there's definitely a geographical kind of distribution. So at this plate margin or boundary, you've got clearly a divergent margin because the South American plate is moving away from the African plate all along the mid-Atlantic ridge. So that's a divergent boundary. Other divergent boundaries there's one here, there's one here as well. Alright, so where I've done a splash of pink, these plates are pulling apart or diverging. You've also got where plates are converging together, which are at these. So these plates are pushing towards each other and are converging, and the main one that we're interested in is this one just here. Less common are where plates are sliding past each other in opposite directions or in the same direction at different speeds. That's a good example where the North American plate is going past the Pacific plate at a different speed, but they're going in the same direction. Right. Right then, so the distribution of earthquakes. You've got this map, I think, on page 3, my lot, but yeah, we need to have a little meat to the bones. Right. Like all geographers, we love to map things. So we've got the plate boundaries shown in blue, alright, and then we've got active volcanoes, the big red dots, and other volcanoes that maybe not have erupted for a while, small red dots. And you know, you can see there's a pretty strong overlap, isn't there, between plate boundaries and where we find. Why have I done the volcano one first? No, we'll do earthquakes first. My OCD will kick in if I don't. Right. So, plate margin in blue, earthquake zones or registered earthquakes that we've plotted, and you can see again there's a pretty strong kind of relationship or pattern. Wherever we've got plate boundaries, we get earthquakes. Wow, what an observation. Yeah, a little fact for you. 70% of all global earthquakes are found around the Pacific Ring of Fire. Alright. And I will talk briefly about magnitude as well, because this is important. You need to write this down, make a note of it. The highest magnitude megathrust earthquakes are found near subduction zones and convergent plate margins. Alright, so where plates are converging together and one plate is subducted under another plate, we get megathrust earthquakes, and they are often the highest magnitude. Alright, conservative plate boundaries or margins, such as the San Andreas Fault, we get shallow focused medium to high magnitude earthquakes. So they're still substantial, cause a lot of damage at conservative plate margins. The lowest magnitude earthquakes we find at divergent plate margins, like the Mid-Atlantic Ridge, just here, and also intraplate earthquakes tend to be lower magnitude. So intraplate just means in the centre of tectonic plates. They're not as frequent and they're lower magnitude. Yep. For instance, I remember being asleep in bed at about 2 a.m. 2007, 2008. I'd just been nightclubbing. I came in nightclubbing and I was dozing off to sleep, and I felt the bed shake. I thought I was having a dream, but I wasn't. I was experiencing kind of an intraplate earthquake because the UK is in the centre of the Eurasian plate. So it was low magnitude. Luckily, it didn't wake me up. I just wondered what on earth were happening, really. Right. Volcanoes, then. Oh, no, quick. No, before I move on. This table shows the largest recorded magnitude earthquake since 1900. So, Chile, 9.5. Alaska, 9.2. Most of these are above 9. Alaska, Chile, Indonesia, Japan, Russia, Chile. So if we map these, here we go. Chile number 1, Chile number 2, Japan, Kamchatka in Russia, I think that's somewhere up here, Indonesia. What was the other one? I can't remember. Yeah, but what you notice is all of these that, over 8.5 in magnitude, or especially 9 in magnitude, tend to happen at subduction zones, all right, where one tectonic plate subducts underneath the continental plate. And we get megathrust earthquakes, which are the highest magnitude and pose the highest risk to people. All right, so synoptic concept risk comes in at this point when we're making a judgment. Obviously, lower risk is at your divergent and intraplate, divergent plate margins and at intraplate locations. You've got lower magnitude, so therefore lower risk. Easy. Right, volcanoes, their distribution, let's have a look. Well, again, similar kind of pattern, isn't it? Yep, a lot of your active volcanoes are again at subduction zones and at convergent plate margins. We also find them at divergent plate margins, like Iceland. Yep, so divergent plate margins. Convergent. We don't find them at conservative plate margins, all right? So earthquakes we find at all 3 plate boundaries and occasionally intraplate. Volcanoes we find at convergent, subduction zones, divergent, but we don't find them at conservative. With volcanoes as well, we do get intraplate volcanoes such as Hawaii, numbers 12 and 10, Mauna Loa and Kilauea, not killer whale, killer whale. And also there's other intraplate ones that pop up a little bit as well, such as Nios in Africa. Right. Tsunamis. Well, if we think about what a tsunami is, it's a series of waves in an ocean caused by the displacement of a large volume of water due to submarine earthquakes, volcanoes, or landslides. So, in a nutshell, submarine earthquakes and the energy they release underwater could cause big waves. Alright? Now, if you want to jazz that up a little bit, tsunami risk is highest along coastlines which are adjacent to or face large expanses of ocean where there's a risk of high magnitude submarine earthquakes. Alright? So for instance, if you have a look at this, you've got the west coast of South America, Central America, moving up to the west coast of the USA, California, Alaska, across to kind of Russia, northern China, Japan, Southeast Asia, Indonesia, even, I guess, the east coast of Australia. All of these coastlines are at risk of tsunamis because it doesn't really matter where the submarine earthquake happens, because the waves can travel across oceans for thousands of miles. Alright? There's not much friction to actually stop the waves. So you can see here that we've had a submarine earthquake happen here, and yeah, the waves are much higher, obviously closer to it, but if you think, people living in Chile and Peru along the west coast of South America will see these waves, hours and hours after they've travelled across the world's largest ocean. Alright? So, tsunami risk is highest where coastlines adjacent to or facing kind of submarine earthquakes, landslides, or volcanoes. Okie dokie. Right. Some key terms then. On page 4, there's a list of keywords, and we can now kind of add some meaning to these keywords. So, we'll start with the most obvious one, which I probably should have kicked off with these, but I like to mix it up a little bit. So, what is a tectonic plate? Well, it's part of the lithosphere, really. The rigid outermost shell of a planet, which is the Earth's crust. And the Earth's crust is not one single piece. The Earth's crust, or the lithosphere, is broken up into 7 or 8 major plates. Now, it is worth getting familiar with the names of these plates, like now. Yeah? When we get to case studies and we're talking about in detail what's happening at different plate boundaries, I am expecting you to be familiar with the South American plate is converging against the Nazca plate, for instance. Yeah, at the Mid-Atlantic Ridge, the South American plate is diverging away from the African plate. When we get to the Sichuan earthquake in China, the Australian plate or the Indo-Australian plate is converging against the Eurasian plate. So, I am expecting you to kind of just be integrating these into your explanations. Yep, little named examples. Okie dokie. So get familiar with the names of the North American, the Nazca, South American, Eurasian, Indo-Australian, Pacific. Yep, 5 or 6 are your major ones. Next key term is, well, what causes these plates to move? Yep. Now then, it's a process of convection. Now, convection is when heat from the inner core of the Earth causes convection currents or cells in the mantle. All right. Make a little note as well what it is that causes this intense heat in the Earth's inner core. It's radioactive decay. Yep. So radioactive decay in the inner core causes convection currents in the mantle, and we get movement in a circular motion, which obviously there's a force there when this is kind of moving. It's going to move the crust around that sits on top of the mantle. Yep. So convection currents in the mantle cause the tectonic plates to move. Simple as that. Right, where should we go next? We'll go to a subduction zone. At a convergent plate boundary, we've got two plates converging together. So in this example, we've got an oceanic plate or crust, and we've got a continental plate or crust moving together. Obviously, two forces collide, something's got to give, or should give, if they're slightly different. Now, the oceanic crust, because it's denser and it's thinner, naturally it gets pushed under or subducts under the continental crust. And I don't even you need to use the word pushed under. I just want you to say it subducts under, right? And this whole kind of area near the boundary where it subducts is called a subduction zone. All right, and it's where we find deep ocean trenches, it's where we find explosive volcanoes, it's where we find high magnitude megathrust earthquakes like Chile. Yep. So subduction zone, when two plates converge together, one is subducted under the other. This happens because oceanic plates are denser and thinner than continental plates. All right, buzz in. Right. This connects to the last one as well. Right. Slab pull. It is not when you're on the pull in a nightclub. That is not slab pull. Slab pull is a geographical term. It's the force that drives the subduction. All right. So in this example, just to confuse you, I've reversed it. We've got this oceanic crust converging from, let's say, east to west, and we've got continental crust converging from west to east. What are the rules? Well, the oceanic crust is denser and thinner, so naturally it gets subducted under the continental crust. All right. When I was at school, my teachers used to tell me wrongly that the force that started this movement off came from ridge push at a divergent boundary. So because of the convection, the plates and the crust spread apart, and that force causes this oceanic crust to be pushed from the ridge towards the subduction zone. However, the last 25 years or so, since the mid-90s, super duper geologists and scientists have realised that the force really comes from the pulling at the subduction zone. All right. And that force is estimated to be approximately 80 to 90% of the force that kind of gets the oceanic plate moving and subducting into the upper mantle. Yeah. So 80 to 90% of the significance of the force is from slab pull down into the upper mantle. 10 to 20% is from ridge push at a divergent margin. Yep. So, yeah, just jot this down, folks. Yep, lovely bit of evidence, that. Lovely bit of evidence. Yeah, so cold, dense oceanic plates sink into the mantle, and slab pull is the force, slab suction as well, accounts for 80 to 90% of the driving of that movement. Okay. The next time you're on the pull, you can be telling your mates, oh, slab pull. Yeah, happy days. Right. The next one is a mantle plume. Sounds really interesting, that, doesn't it? Right. Mantle plumes and hotspots are kind of linked, so I've done them both together. And these are crucial when thinking about intraplate processes. All right. Now, intraplate means the center or middle of a plate. Now, if we have a look, what is a mantle plume? Well, it's an upwelling of super hot rock within the Earth's mantle. All right. And it's like a narrow column of super hot rock that's risen from the Earth's outer core. And when it breaks the surface, we get new land formed, all right? Because that magma or that plume breaks the surface, meets cold ocean water, and solidifies into islands. And these islands are volcanic islands or hotspots, all right? Now, so your mantle plume causes your hotspot. They are inextricably linked. Yep. So hotspots are volcanic regions which are fed by mantle plumes. There's no better way to kind of do this than to do a little sketch. Really simple sketch, yeah? Super hot, narrow column of hot rock. Breaks the surface, causes a hotspot. And that's one explanation for intraplate volcanoes, or volcanic island chains like Hawaii. Because what's happening in Hawaii is we've got a hotspot underneath this island here, and the hotspot stays fixed in its location. The only thing that changes or moves is the crust that sits on the top of it, right? So you just visualize it. The hotspot keeps breaking through the surface, but the crust above it moves slowly above it. What you're going to get is a series of islands, all in a line, right? And that's what we've got here with these Hawaiian islands. So the older islands like Oahu, yep. Next youngest, Molokai, then Lanai, then Maui, then Hawaii. And that's because the Pacific plate is moving northwest. Yep. Right, folks. I think that will do. Just make sure you are capable of filling in everything, and you make sure you fill in everything, and everything's sketched in your booklets up to page 7. Yep. And this video and a little bit of reading around and problem solving should enable you to do that. All right. Happy days. I think I might book an holiday to Hawaii actually and get me Beach Boys surfer dude haircut ready and my nice Hawaiian pink and yellow shirt and my board shorts and my surfboard. Yep, I'm on it. I'll see you next year. See ya.